Hello everyone. In this video, I'm going to walk you through the R codes that will help you do these tree-based models. I'm going to load this package tree, which will help us, from which we will use a tree function to create the decision trees. And we need the ISLR2 package for the data sets. So we load these libraries. We are going to use the car seats data first to do the decision tree. And what I'm going to do is I'm going to create an additional categorical variable, high, which will take the value 1 if sales is greater than 8 and 0 otherwise. And I'm going to attach that variable to the car seats data. And creating a tree is absolutely straight as an arrow. You use the tree function, specify your response variable, tilde dot means every other predictor goes in, every other variable goes in uh, as as potential predictor. I'm removing sales from the prediction because this is actually captured in the response variable. And because this is created out of sales, it doesn't make sense to include sales as a potential predictor. So I have that. I can get the summary, which is not that intuitive. So you can see that there are 27 number of terminal nodes. And misclassification error is 36 out of 400. So it gives you some interesting stats. But we are here more for the graphs, right? So we use the plot function and we use the text to add everything in there. And we have our tree first up. Yes. So we have our first tree, which is a single decision tree. So what it says is that at the first node, the single most important predictor is shelf life. Then you have the price. If it is less than 92.5, then what matters is income. If it's less than 57, then these two factors. If it is not, then you end up over here. Advertising, if it is less than 13.5, then comp price. If it is less than 124.5, then again price. And this is how you create a decision tree, a single decision tree. To evaluate the performance, we need to split the data into training and testing. We set the seed, set aside 200 observations as training, the remaining as test, and we redraw the tree and we look at the accuracy. So this 0.77 means 77% of the time our predictions are accurate, which is a pretty good number. To do the cross-validation, we use the cv.tree function that allows for doing the tree with cross-validation. And we see that these are the variables. These are the important information that goes in there. And we can plot that. So set up the margin. So this is the so now we have two figures. The first one is we are plotting the size of the tree against a cross-validation error. And in the second one, we are plotting the complexity parameter against a cross-validation error. So that's there. We can prune the tree as well using the prune.misclass function. And we now have a shorter version of the tree. And we can evaluate the prune tree or the test set, and we can see that our accuracy is 77.5%. So it's not that big of an improvement. But still it's there. So next up, we are going to look at the bagging. We are going to fit a regression tree into the Boston data set, and we are going to set the seed and create a training set. And we have that over here. And we can do a cross-validation and plot that as well. And you can see that the errors continuously goes down as we increase the size of the tree. And this is a shorter version of the tree that we get from cross-validation. We can make predictions using the predict function on the test set, and this is what we get. We can calculate the mean square error. So that's there. But for the bagging and random forest, we need the random forest library. Load that, set the seed. The random forest is, we use the random forest function, and m try equals 12 means all 12 predictors are considered for each split. So this is bagging essentially, and the importance equal true allows us to access the variable importance later. So we fit the model, make the predictions, and plot the predicted value against the actual values. We can calculate the mean square error, and we can also do another bagging model with fewer trees because the default is 500. And we see that the error is actually increased a little from 23.12 to 23.84. The difference between bagging and random forest is that we have to work with a smaller set of predictors. We can't use all the predictors every time. And now we have the importance of each of these factors over here. So RM is the most important factor with 32.34%. Then we have the LSAT, and then we have crime. So these are the more important predictors in this model as compared to the other predictors. And you can also plot that using the var in plot function. And this is basically the table that I showed you in a graphical form. For boosting, we need the GBM library. And once we run the codes, so this shows how the predicted response changes as a function of the input variable, which in this case is LSAT. We also have a similar plot for RM. And again, we can make predictions and calculate the mean square error. It is 18.18, so slightly lower than bagging or random forest. There is this BART model which is there in the text. I'm not covering that in this chapter, in this course, but you are most welcome to try them out on your own. And yeah, so that's about it. So again, the thing over here is that as far as our coding is concerned, it's not that complicated. So because the functions are already there. What you need to focus more on is how these methods work from the theory side, so that you know what exactly to code, because whatever you need to code, it's already there. You don't need to manually type something up. You don't need to write a function. You don't need to create your own statistic. You just need to use the right function with the right arguments, and for that, the theoretical understanding is most important. So I hope this was useful. And again, do not hesitate to let me ask any questions if you have. Thanks.